Good morning. I'd like to make an advice. We change a little the program in order to have more free time tomorrow. So Professor Natasha Sessun talk will be the next day, okay? You will receive an email with the changing, informing the changing, okay? The first talk of this morning is Professor Luis Alias from Murcia's University. He's going to talk in geometric application of the generalized or Marial maximum principle.
Thank you very much. Well, first of all, I'd like to thank to the organizing committee of the conference for giving me the opportunity to participate in this conference and celebrate Marcos' birthday. In this lecture, I'm going to speak about several results which has to do with geometric applications of the generalized or Moriyama maximum principle to the study of the geometry of some manifolds, both in Riemannian and in Lorentzian spaces. And this is part of my joint work with several colleagues, Pacelli Besa from Fortaleza, Marcos Dajczer, Ana Hurtado from Granada in Spain, Fabio Montenegro from Fortaleza, and Vicente Palmer from Castellón, also in Spain. Okay, we'll start by reviewing some basic facts about the known or Moriyama maximum principle. Consider M a compact Riemannian manifold without boundary. Then it's clear that for any smooth function on M, there exists a point where the function attains its maximum, and in particular, at that point, we have that the u at x dot is the maximum of the function, the gradient vanishes, and the Laplacian is non-positive. Or more generally, the Hessian of the function at point x0 is non-positive semi-definite in the sense that for bilinear forms. Obviously, if M is not compact, then that is not true in general. So in general, given a function which is bounded from above, we cannot find a point where the function attains its supremum. But, for instance, in Rm, it can be seen that if you take a smooth function on Rm which is bounded from above, then we may find a sequence of points satisfying the following conditions. So essentially it's a sequence of points in Rm converging to the supremum of the function. The gradient converges to 0, and the Laplacian at each point xk is less than 1 over k. So in the limit, if that sequence converges, it should converge to the point where the function attains its maximum. But in general, it does not exceed that point. Or even more generally, we can also replace this condition 3 by 3 prime, which is the condition on the Hessian of the function. To prove this, essentially you take a sequence of positive epsilons decreasing to 0 and choose at xk the point where this function attains its maximum. I say essentially because it's necessary to take a subsequence of that sequence, but essentially that's the idea, how to find the sequence xk. In 1967, Omori realized that this property is not true for a general complete Riemannian manifold, and he found explicit examples of actually metrics on R2 which are complete and do not satisfy this condition. But one needs to impose some geometrical conditions on M to get the validity of that property. And specifically, he proved that if you consider a complete Riemannian manifold with sectional curvature bounding from below, then the property holds for the condition 3 prime, for the condition on the Hessian on the function. So for any function bounding from above on M, you may find a sequence of points satisfying these 3 conditions. Later on, Yau extended it for complete Riemannian manifolds with Ricci curvature bounded from below and replacing condition 3' by condition 3 on the Laplacian of the function. So for complete Riemannian manifolds with Ricci curvature bounded from below, this is also true, the existence of that sequence. For that reason, and following the terminology introduced by Pigola, Rigoli, and Setti, we say that the Omori-Yau maximum principle holds on a Riemannian manifold if for any smooth function which is bounded from above, we may find a sequence of points satisfying the three conditions. That one on the gradient, and that one on the Laplacian. Equivalently, we can also state the same, but for functions bounded from below, replacing the supremum by the infimum and changing the inequality on the Laplacian. In this sense, the maximum principle given by Omori and Yau states that the Omori-Yau maximum principle holds on every complete Riemannian manifold with Ricci curvature bounded from below. More generally, as observed by Pigola, Rigoli, and Setti, the validity of the Omori-Yau maximum principle does not depend on curvature bounds as much as one would expect. And, in fact, they gave a generalization of theorem 1 above as follows. They prove that the Omori-Yau maximum principle holds on every Riemannian manifold, admitting a non-negative C2 function satisfying the following requirements. First, the function psi goes to infinity as x goes to infinity, in the sense that it leaves the compacts of M. Second, there exists a positive constant such that the gradient of the function psi is bounded from above by this constant square root of psi of a compact set on M. And the third condition, we need also a control on the Laplacian of psi. There exists a positive constant b such that the Laplacian of psi is bounded from above by b and this function of a compact set of M, where g is a smooth function satisfying these technical conditions. So that's what we call the generalized Omori-Yau maximum principle. And this generalized Omori-Yau maximum principle, in fact, because, for instance, if we assume that M has a sufficiently controlled decay of the radial Ricci curvature in this form, where here rho is the distance on M to a fixed point, C is a positive constant, and G is a function as above, that is enough to have the Omori-Yau maximum principle, which is much weaker than asking the Ricci curvature being bounded from below, of course. Actually, in that case, taking upside the square of the distance, we get the validity of the Omori-Yau on such a manifold. On the other hand, if we assume that M is a Riemannian manifold which is properly immersed into another Riemannian manifold N by the immersion phi, then if we assume that the radial sectional curvature with respect to a fixed point in the ambient space is bounded from below in this form, where here hot rho is the distance in the ambient space, and if the immersion does not intersect the cut points of P and has control mean curvature in this form, then again, taking this function as psi, we get the validity of the Omori-Yau maximum principle in such as a manifold. For instance, in particular, the Omori-Yau maximum principle holds for every submanifold which is properly immersed with bounded mean curvature into a Riemannian space form. Okay, so our objective in this lecture is to give some geometric applications of this generalized Omori-Yau maximum principle for in different ambient spaces. We will start considering cylindrically bounded submanifolds in a product space. We consider psi an isometric immersion from a complete Riemannian manifold M of dimension M into a product space of the form N times RL, where N is a complete Riemannian manifold of dimension N minus L. In this context, we say that M is cylindrically bounded if the projection of the immersion M onto the factor N is bounded. That is, if there exists a geodesic ball in N such that the image of the immersion is contained in this solid cylinder. Here and in what follows, we will assume that M is cylindrically bounded and that the radial sectional curvature of the ambient space along the radial geodesics issuing from the center of the geodesic ball containing the projection of the immersion is bounded from above by a number B. We will also assume that the radius of the geodesic ball is less than this quantity if B is positive and this quantity if B is non-negative as usual. And also as usual, we will denote by CBT these functions in the cases where B is positive, B is 0, and B is negative. So with this notation in mind, we can state our first result, which is the following. Consider a proper and cylindrically bounded isometric immersion such that the image is contained in this solid cylinder and M minus L is bigger than 1. We assume that condition on the curvature of the ambient space, as I already said. Then in that case, we can estimate the supremum of the mean curvature from below by this quantity here. This theorem, first of all, extends to complete submanifolds. The main results given by Besa and Montenegro for compact hypersurfaces. They consider compact hypersurfaces in a product space of the form N times R, and in particular, it extends the following result, stated by Besa and Montenegro, which answers in the affirmative a question suggested by Rosenberg in 2005, which has to do with the estimation of this value here, which is the infimum of the mean curvature over the set of all possible compact constant mean curvature immersed into the ambient space. And in particular, when N is the hyperbolic space, they obtain this bound, which was actually conjectured by Harold in 2005. Also, as another application of our theorem, we obtain the following consequence for hypersurfaces in Euclidean space. We prove that if we consider a complete hypersurface in Euclidean space, and we assume that the projection of the immersion onto a two-dimensional subspace is bounded, then the supremum of the mean curvature is bounded from above by this, and the supremum is bounded from above by this quantity, then the immersion cannot be proper. Observe that this bound on the supremum of the mean curvature is sharp, because that's exactly the mean curvature of the cylinder. And in particular, if the mean curvature is 0, we obtain that a complete minimal hypersurface having bounded projection in a two-dimensional subspace cannot be proper. Related to this, Saer and Rosenberg proved earlier that every complete minimal hypersurface with bounded projection in an n-1 dimensional subspace cannot be proper. And in this respect, we'd like to recall Calabi's conjecture on minimal hypersurfaces, which were presented by Calabi in the 60s and promoted by Chen about the same time. There are two conjectures. The first conjecture says that any complete minimal hypersurface in Rn must be unbounded. And the second conjecture says that any complete non-flat minimal hypersurface in Rn has unbounded projections in every n-2 dimensional subspace. With respect to these two conjectures, it's known that the immersed version of both conjectures are false in R3, actually. First, Jorge and Javier, they gave an example of a non-flat, complete minimal surface, which is bounded between two parallel planes in R3, so contradicting the second conjecture. And later on, Nadirashvili gave a complete minimal surface which is inside a round ball in R3, contradicting then the first conjecture. Very recently, Koldin and Minikossi have shown that both conjectures hold true for embedded minimal surfaces in R3. It's worth pointing out that the immersed counterexamples to both conjectures above are non-proper. So it's natural to ask if any possible higher dimensional counterexample to any of Calabi's conjecture must be non-proper. And actually, as a consequence of our result, we obtain that any possible counterexample to the second conjecture must be non-proper, because since if the immersion is contained in this solid cylinder, then it is contained also in this other solid cylinder. So that's another nice application of our result. Now I would like to give an idea of the proof of the result to show you how we use the maximum principle to prove these kind of results. Well, the idea of the proof is the following. We consider the function u, which is just the distance on n of the projection of the immersion onto the factor n. So that's the function u. We just take the projection of the immersion onto n and take the distance to the point P. Since we are assuming that the submanifold is cylindrically bounded, then we know that this function is bounded from above. So the idea of the proof is to apply the Omori-Yau maximum principle to that function. But first, we need to check that the Omori-Yau maximum principle holds on M. To see that the Omori-Yau maximum principle holds on M, we consider the function psi, the following, which is the distance, the Euclidean distance of the Euclidean projection of the immersion onto the factor RL. This gives a positive, positive function. And first of all, since the immersion is proper and M is cylindrically bounded, then psi of x goes to infinity as x goes to infinity in M. So we have the first condition in theorem 2. We need to check the three conditions to be able to say that M actually satisfies the maximum principle. So that's the first condition. For the second condition, there is also no problem, because of a compact set, observe that the gradient of psi is just the tangent part of the gradient of this function, which is the Euclidean distance. So, and this gradient is 1. So this gradient is bounded from above by this, and of a compact set is bounded from above by this function, which goes to infinity. So that is no problem. And now we have to check the third condition on the Laplacian, and for that we need to compute the Laplacian of psi. To compute the Laplacian of psi, we first observe that actually, since the function of psi depends only on the projection on the Euclidean space, we can compute it as this, using just the Gauss formula. We can express this as this term plus this term where it appears the mean curvature vector field of the immersion. So now we need to work with this term here to be able to estimate the Laplacian of psi from above. And for doing that, we consider polar coordinates on n, and also polar coordinates on Rn, which are orthogonal at our point. And then we may write any orthogonal basis for M at the point X in that basis as follows. So that's the radial direction that they are orthogonal to this direction. This is the radial direction in RL, and those are the orthogonal directions to this radial direction. And hence, we can compute the Hessian of the Euclidean distance on the projection of EI as this, and this is bounded from above by this quantity, because this here is bounded from above by 1 just from here. Okay, this BIT is just this part of the vector EI, which is unitary vector. So we have that, and also since the function psi x goes to infinity, then of a compact set, we may assume that the norm of the mean curvature vector field is bounded from above by a function like this, where G is this function. Otherwise, the supremum would be infinity, and there is nothing to prove. So, and also besides of a compact sets, we also have this condition thanks to the conditions for the function G. So putting together all this, we can estimate the Laplacian of psi by this, and this is bounded from above by this quantity here. So at the end, we get that the third condition of psi holds also, and then we know that the manifold M satisfies the maximum principle. Now we are ready to apply the maximum principle to the other function. To do that, we recall that U is just the distance on the projection on the factor N, and by the maximum principle, we know the existence of this sequence satisfying 1, 2, and 3. But from 3, then we have that 1 over k is bigger than this quantity here, and now again we can compute the Laplacian of U, taking into account that now the function U depends only on the factor N. So we can compute it, and here it appears the Hessian of the distance in N, and the gradient and the mean curvature vector fields. Now we have to work with this, and here we have not used yet the condition on the curvature of the ambient space. Here is where we need to use it to estimate this Hessian. We start with polar coordinates on N and with the standard coordinates in the Euclidean space, and then again we may write any orthonormal basis now in using this basis of the ambient space. And then using the Hessian comparison theorem, we can estimate from below the Hessian of the distance function by this function CB, and this gives us this estimate here. And working a bit more, we can, of course, we can also estimate this by this just because this is a unitary vector, and we observe that this sum here is just the norm of the gradient of U, which is just the tangent part of the gradient of the distance in the manifold N, and we know that it is bounded from above by this quantity here. And finally, we observe regarding this other term here, this is just the sum of this, which is bounded from above by L, which is just the number of summands here, because each summand is bounded from above by 1. So putting together all this, we obtain this chain of inequalities, and now letting k goes to infinity, we conclude the result. And this finishes the proof of our first main result. Okay, now let us say something about the sectional curvature of cylindrically bounded sum manifolds. In 81, and as an application of the classical Omori-Yau maximum principle, Jorge and Koutroufotis obtained the following result, which is well known. We consider M and N complete Riemannian manifolds of dimension M and N, and we take a bounded isometric immersion such that the image is contained in a geodesic ball of radius r, and we have this bound for the dimension and this relation between the dimension of n and the dimension of m. Then under the assumption that the radial sectional curvature of the ambient space is bounded from above by B, if the scalar curvature of M is bounded from below, then we can estimate the supremum of the sectional curvature of M by the infimum of the sectional curvature of M in the ball plus this function here. This result implies and extends several older non-immersibility results for compact Riemannian manifolds due to several authors, which can be summarized as follows at the end. And now it's a corollary of theorem 4. We consider M and N the geometric measure of a compact Riemannian manifold into a Cartan-Hadamard manifold with non-positive sectional curvature. Then the supremum of the sectional curvature of M is bigger than the infimum of the sectional curvature of M. By using the generalized Omori-Yau maximum principle, theorem below, theorem 4 above, can be stated more generally under the assumption that the scalar, recall that here we assume that the scalar curvature is bounded from below. We can weaken this condition, we can make that condition weaker, just replacing and asking that the scalar curvature is bounded from below by a function like this. And that's enough to apply the maximum principle and get the result. So following this idea and as another application of our method, we have recently obtained the following extension of Jorge Coutrofotti's theorem to the case of complete cylindrically bounded submanifolds, which is the following result. We consider an isometric immersion into a product, Riemannian product space, which is cylindrically bounded, such that the projection onto the factor n is contained in a ball of radius r. And then under the same assumptions as in Jorge Coutrofotti's theorem, we can obtain the same result, the same estimate for the sectional curvature. I'm not going to give the details of this, the proof of this theorem, but essentially the proof follows by applying the maximum principle to, not to the function u, but to an appropriate function of u, and using again Hessian comparison theorem and Otsuki's lemma. Okay, now let us see what is the weak Omori-Yau maximum principle. The weak Omori-Yau is said to hold on a Riemannian manifold if, for any function which is bounded from above, we may find a sequence of points satisfying only condition 1 and 3. As proved by Pigola, Rigoli, and Setti, the fact that the weak maximum principle holds on a Riemannian manifold is equivalent to the so-called stochastic completeness of the manifold. Here we recall that a Riemannian manifold is said to be stochastically complete if for some, and therefore for any xt, we have that the integral over M of the Hith kernel of the Laplacian operator is equal to 1. There are many conditions which are equivalent to the stochastic completeness of the manifold, and for us this is equivalent, among other conditions, to the fact that for every positive lambda, the only non-negative bounded smooth solution to this inequality is the constant function u equal to 0. So in particular, every parabolic Riemannian manifold is stochastically complete. And as a consequence, the weak maximum principle holds on every parabolic Riemannian manifold. So, also as an application of our method, we can obtain a result about stochastic uncompleteness of cylindrically bounded submanifolds, which extends previous results. In 1989, Mark Borsen derived a mean time exit comparison theorem, which implies that every bounded complete minimal submanifold of a Cartan-Hadamard manifold is stochastically incomplete. This result has been recently extended to the case of complete cylindrically bounded minimal submanifolds in this product space. And in our following result, we are able to extend this to the case of complete cylindrically bounded submanifolds in here, not necessarily minimal, but with sufficiently small mean curvature. And the theorem is the following. Consider an isometric immersion, which is cylindrically bounded as this, and under the same assumptions as in our previous main result, we prove that if the supremum of the mean curvature is bounded from above by this quantity, then the manifold is stochastically incomplete. The proof of this theorem is as follows. We suppose, on the contrary, that M is stochastically complete, and consider this function f, which is a function of the distance. Here, u is again the distance of the distance function of the projection on the factor n, and we consider this function f, which is psi of b of u, with this choice for phi. Since we are assuming that M is stochastically complete, then we may apply the weak maximum principle, and by the weak maximum principle, there is a sequence of points satisfying condition 1 and condition 3 for the function f, which is bounded from above by this quantity here. Now, doing now a similar computation as we did in the theorem, in theorem 3, and taking into account that this function satisfies the following differential equation, then we can obtain the following. We have first 1 over k bigger than this from the weak Omorija maximum principle, and again this we may compute this Laplacian in terms of the Laplacian of the Hessian and the gradient of on the manifold n, again because the function f depends only on the factor n, and we can estimate this doing a similar computation as in theorem 3 by this quantity here. So at the end we get this inequality, and now letting k go into infinity, we obtain the result. And this finishes the proof of theorem 6. Okay. Now in the second part of my lecture, I'm going to speak about some application of the maximum principle for specialized hypersurfaces in Lorentzian space. For doing that, I need first to introduce some basic things about the Lorentzian distance function, which is not so well known as the Riemannian distance function. So we have to change our mind a bit to forget about Riemannian intuition and going into the Lorentzian world. So we consider n bar and n plus 1 dimensional. Here I will use n plus 1 for the dimension of the ambient space because I will consider only the case of hypersurfaces. So we consider an n plus 1 dimensional spacetime, which is just a Lorentzian manifold which is time oriented and dimension at least 2. We consider P and Q 2 points in n bar, then using the standard terminology from Lorentzian geometry, we say that Q is in the chronological future of P, and we write it like this. If we can reach Q from P via future-directed time-like curve. There exists a future-directed time-like curve going from P to Q. Here, future-directed means that the velocity of the curve, which is always a time-like vector, is points in the future of m bar. When we say that m is time-oriented, that means this is equivalent to the existence of a globally defined time-like vector on the ambient space, and that globally defined time-like vector allows us to speak of the future and the past. So when we say future-directed, we mean that the time-like direction points in the same direction as that globally time-like vector defined on the ambient space. Similarly, we say that Q is in the causal future of P, and we write it like this, if there exists a future directed causal curve going from P to Q, where causal now means which is not space-like. So it could be time-like or could be light-like, but not space-like. So again, the velocity vector of the curve is either time-like or null vector, and points always to the future. Obviously, if Q is in the chronological future of P, then Q is also in the causal future of P, and as usual we say that P is less than or equal to Q if either P is less than Q or they are equal. Now, if we consider a subset, an arbitrary subset on the space-time M bar, we can define the chronological future of S as the set of all points which are in the future of any point of S. So I plus of S is the set of Q for such that there exists some point P such that Q is in the chronological future of the point P. And we define also the causal future of S, which is denoted by J plus S, the same, but replacing chronological future by causal future. So in general, S union the chronological future of S is contained in the causal future of S. In particular, the chronological future of a point, when the subset S reduced to a point, we had the chronological future I plus P and the causal future J plus P of a point, which is just this and this. And there are some general properties of these subsets. For instance, I plus the chronological future of a point is always open. However, the causal future of a point in general is neither open nor closed. And now we are ready to define the Lorentzian distance. When you are in a Lorentzian ambient space, you cannot define the Lorentzian distance as the infimum of the length, because that is always 0. So in this case, we consider first, we fix a point P. Then if we take a point Q which is in the causal future of P, we may define the Lorentzian distance as the supremum of the Lorentzian lengths of all the future directed causal curves going from P to Q. This is possibly infinity. Okay? The infimum of these quantities would be 0, because you may always find a curve which is almost light-like going from P to Q, and then the infimum is always 0. So the supremum defines the Lorentzian distance. But of course, we can do that only if there exists causal curves going from P to Q. So what we do for the other points, if Q is not in the causal future of P, then the Lorentzian distance is by definition is 0. And that is the Lorentzian distance, which has nothing to do with a distance. Okay? So actually many people don't like to call it distance, but I like it. So, but for instance, it's not symmetric and it's very funny distance. Okay. In particular, for instance, we can see that this distance is positive if and only if Q is in the chronological future of P, and this gives a function which in general may fail to be continuous and may fail also to be finite valued. So in general, it's a very bad function. As a matter of fact, globally hyperbolic spacetimes are the natural class of spacetimes for which this Lorentzian distance behaves quite well. Here, a spacetime is said to be globally hyperbolic. This is two conditions. First, it is causal in the sense that there is no causal loop in the manifold, and the second condition has to do with the compactness of the diamonds. That means that you take a point P and a point Q, and then you take the intersection of the causal future and the past future, the causal future of P and the past future of Q, which is something like a diamond. They are compact. That is the condition. There are other equivalent and maybe more intuitive conditions, but we don't bother about that now. Okay. The point is that there exists a very wide class of spacetime where the distance behaves well. And now, if we fix a point P in our Lorentzian manifold, we can define the Lorentzian distance from P just as this function. And our objective now is to do some geometric analysis using this distance. So we need to work on subsets of M where that distance is smooth. So to guarantee the smoothness of this of the Lorentzian distance, we need to restrict this to certain subsets of the ambient space. And for doing that, we start with the following. We denote by T minus 1 M bar is the fiber of the unit future observed bundle of M bar, which is just the set of all vectors which are tangent to M bar at point P, which are future directed time-like unit vectors. And for that subset, we may define the function SPV, which is we fix a point P, we fix a future vector V, and then take the geodesic starting from P with velocity V, and we stop at the point where the Lorentzian distance for little t, the Lorentzian distance is realized in the geodesic, but there is a point, just as in the Riemann case, where it stops to realize the distance, and that's the point, that's the value of SPV, the supremum of t, such that this equality holds. Okay? And then we can define this subset I plus tilde, which is the for every future directed B, we take this is a star set subset around the origin. For every direction B, we take the vector TV where T goes is between 0 and this value SPV, which is the value at which the distance stops to real, at which the geodesic stops to realize the distance. Okay, and now finally we consider the diffeomorphic image under the exponential map of the interior of this subset, and that is the subset where we can assure that the distance is smooth. So that's why we call this subset the smooth chronological future of P. And there is a result which assures that under some nice conditions on the ambient space, those subsets are non-empty and the Lorentzian distance function is smooth. In general, if the ambient space is strongly causal, which is something strong than being causal, obviously. Being causal is not admitting causal loops. This is something little strong. But essentially, with this condition, we know that this SPV is positive for all B, and this subset is not empty. And when this subset is not empty, then the Lorentzian distance function is smooth, and we can work well with that function. So now we know where we can, since we want to do some geometric analysis of spaces like hypersurfaces in these ambient spaces, we know that we need to ask the hypersurface to be contained in this kind of subsets. Well, first we need to establish the corresponding Hessian and Laplacian comparison results for the Lorentzian distance, and we can do it with not a hard work, but first we need to introduce these functions fc of s, which are the comparison functions in the Lorentzian case. it is interesting to observe that this function appears when we compute the index of a Jacobi field along a time-like geodesic in a Lorentzian space form with constant curvature C in this form, and also Fc of S is the future mean curvature of the level sets of the distance function. So that's the geometric interpretation of this Fc. When I see future mean curvature, I mean the mean curvature with respect to the future pointing normal to the hypersurface. And then we can state that we need three Hessian or two Hessian and one Laplacian comparison results. That the first one, which is under the assumption that the spacetime that this is the sectional curvature for all time-like planes in M bar. So this is under the assumption that the sectional curvature of time-like planes is bounded from above by a constant C. Then, if we are in the smooth future of P, we can estimate the Hessian. This is the Lorentzian Hessian of the Lorentzian distance from below by this quantity. In a similar way as in the Riemannian case, but with the reverse inequalities. This condition, the condition that the sectional curvature of time-like planes is bounded from above, implies that the Ricci curvature of the ambient space on time-like vectors is bounded from below by this quantity here. And this condition, which is weaker, in particular when C is equal to 0, is when it's the so-called time-like convergence condition. So under this other more general condition, we can also give a Laplacian comparison result for the Lorentzian distance, now replacing the condition on the sectional curvature for the condition on the Ricci curvature for time-like directions, and then we get the result for the Lorentzian Laplacian of the distance. And finally, the last comparison result is in the case where the sectional curvature of time-like planes are bounded from below by a constant, and in that case we have the corresponding result with the reverse inequality. Okay. The proof of lemmas 2, 3, and 4 follows from the fact is similar to the proof in the Riemannian case, because in that case we have that the Hessian of the distance is just the index form along the geodesic, the radial geodesic. On the Jacobi field, but here at the end we obtain the reverse inequality because in a Lorentzian manifold, Jacobi fields maximize the index. They don't minimize but maximize the index, and that's why we obtain the reverse inequalities with respect to the Riemannian case. Now we are ready to state our main results here. Well, first, sorry, no, just something about space like hypersurfaces. We will consider now a space like hypersurface immersed into spacetime. Here by space-like we mean that the metric induced on M by the Lorentzian ambient space metric is a Riemannian metric on M. Since the ambient space is time-oriented, there exists a globally defined time-like vector on the ambient space, and the immersion is space-like, then there exists a unique future-directed time-like unique normal field nu globally defined on the hypersurface, and we will consider always this orientation, and that's what we call the future mean curvature, is the mean curvature with respect to this orientation. We assume now that our immersion is contained in the smooth future of a point P, and then we can restrict the Lorentzian distance along the hypersurface, and we can work now with this, which is a smooth function on M, and then using the Hessian and Laplacian comparison results above, we have the three inequalities. First, if we assume that the sectional curvature of time-like planes is bounded from above, then we get this inequality for the Laplacian. This is the Laplacian on M, the Riemannian Laplacian of the restriction of the Lorentzian distance along the hypersurface. This is under the assumption that the sectional curvature are bounded from below, and this is with the condition on the Ricci curvature. And these three inequalities are the inequalities that we will use to prove our main results. Now this is the first main result. Assume that your ambient spacetime satisfies that condition on the Ricci curvature of time-like directions. Then if we have a space-like hypersurface which is containing the smooth future of a point P intersection, this which is the future inner ball of radius delta. This is just the set of points which are in the future of P at a distance less than delta. Okay. If to make an idea of this, you may think that your ambient space is just the flat Minkowski space. In that case, if you fix a point P, then the future of P is just the cone, the upper cone with vertex at P, and the level sets of the distance function they are just hyperbolic spaces centered at the point P, and so the future inner ball would be the region of the Minkowski space which is bounded from above by one hyperbolic space. Okay, that's so. If we assume that our hypersurface is inside this set and the Omori-Yau maximum principle holds on M, then we can estimate the infimum of the mean curvature of M by this quantity here, which is just the mean curvature of the level set at the distance at this distance. Okay. The proof of the theorem follows just applying the Omori-Yau maximum principle to this function. We know this inequality. I'm not going to give the details because I have no much time, but it's just applying the Omori-Yau to this function. We are assuming that the Omori-Yau holds. We are just assuming it. Later on, we will see that when the ambient space has constant curvature, then every space-like hypersurface with bounded mean curvature satisfies the Omori-Yau maximum principle. But for the moment, I'm just assuming that by any reason the maximum principle holds. So it's just playing with this inequality here, and now taking limits when k goes to infinity, and from offset that in this inequality is if k goes to infinity, this goes to 0, this goes to the supremum, this will go to 0, so the denominator will go to n, and here this term, this will go also to 0 because of this condition here. Okay. And now the other result is for the case where the sectional curvature of time-like planes are bounded from below by a constant. In that case, we only need to assume that the hypersurface is in the future of P. We don't need to assume that it is bounded from above. In that case, then we can estimate the supremum of the mean curvature by this value, which is exactly the mean curvature of the level set at the infimum of the function. This infimum could be 0. So as a consequence of this, because we are not assuming that the hypersurface is bounded neither from above or from below. So as a consequence, in particular, if the infimum is 0, which means that the hypersurface approaches to the, for instance, in the Minkowski space, that means that the hypersurface approaches to the light cone. So if the infimum is 0, then the supremum of the mean curvature must be infinity. So as a corollary, if, under the assumption of this theorem, if the mean curvature is bounded from above, then the hypersurface cannot approach to the light cone. In other words, there exists some delta such that the hypersurface remains in the future outer bore. There exists some positive delta such that the hypersurface cannot approach to the light cone. There is a distance, a positive distance between the hypersurface and the light cone. And to prove the result, we just use the Omori-Yau maximum principle again, and take limits, okay? And just to finish, in the previous results, we are assuming that by any reason the maximum principle holds on the manifold. Here, we will consider the case when the hypersurfaces are in a Lorentzian space form, in a Lorentzian space-time with constant sectional curvature. In that case, we can put together both results, and if we have a hypersurface which is in the future of P and bounded from above by a level set, then we have the chain, this chain of inequalities going from the infimum of the mean curvature to the supremum of the mean curvature. And in particular, if M is a complete space-like hypersurface with constant mean curvature, which is contained in the future of P and bounded from above, then it is necessarily a level set, because in that case, since the hypersurface is complete and the mean curvature is constant, then we can assure that the Omori-Yau maximum principle holds, and then we have the equality in this chain of inequalities. Actually, the proof is just that follows just from the Gauss equation of a space-like hypersurface in a general space-time, which goes as this. And in particular, if the ambient space has constant sectional curvature, then the Ricci curvature of any space-like hypersurface is always bounded from below by this quantity. So in particular, if the mean curvature is bounded, the Ricci curvature is bounded from below. Every space-like hypersurface with bounded mean curvature has Ricci curvature bounded from below. This is one of the key points, for instance, to prove the Bernstein theorem for maximal hypersurfaces in Minkowski space, because actually this is also a nice application of the Omori-Yau maximum principle. And the point is that every maximal, which means mean curvature 0, every maximal complete hypersurface in Minkowski space satisfies the Omori-Yau maximum principle. And the proof given by Chen and Yau in the 70s of the Bernstein theorem for higher dimensional maximal hypersurface is essentially to apply the Omori-Yau maximum principle to the square norm of the second fundamental form of the hypersurface. So that is, I mean that in the context of, that is also another reason why in the context of space-like hypersurfaces, we can find many applications of the Omori-Yau maximum principle. So as a corollary, for instance, we obtain that the only complete space-like hypersurfaces having constant mean curvature in the Minkowski space, which are in the future of a point, that means in the cone, they are contained in the cone, in a cone with vertex at P and bounded from above by a hyperbolic space, are just the concentric, the hyperbolic space is centered at the same point. And I think that's all. Thanks a lot for your attention. And also thanks, Marcos, for sharing your knowledge and love for differential geometry with all of us. Thank you very much.